going to be a huge part of what we do in the future. You know, obviously nobody's going to be an expert after 1-2 hour training today, but again, this is, you know, intended to start getting your feet wet and teach you how to use the resources and start getting you thinking about how these things function. System components. We're going to cover the main system components and how to troubleshoot each one. You know, certain parts of the mini split just scared the bejesus out of people. The inverter, that's the thing that's the scary thing, an inverter, right? It's really not that scary. We're going to talk about it. But every time there's a problem, everybody wants to change the inverter because, well, that must be what's wrong because that's the part we don't understand. It's really not that scary. So we're going to talk about the inverter. Controls overview, error code identification, where to find the error codes, what to do with it, what some of the really main error codes are, and then getting into troubleshooting. The biggest thing on these units is as we get into troubleshooting, I know our first immediate response when we don't understand a piece of equipment is call for help. Well, like I just said, we're all here. There's 5 of us. We'll be down to 4 at the end of the year, but there's currently 5 of us available. And we're here to help you. But if you keep reaching out to us, you know, we can help you. But ideally, what you're going to need to do is start to familiarize yourself with these so that you can start, you know, at least trying to troubleshoot them on your own. And I know it's still new. It's all the electronics in it just can be a little frightening. But until we start diving into these on our own, we're not going to learn them. That's just a fact of it. So end of the day, this is still just an air conditioner. We all hopefully understand air conditioning. It's a really advanced air conditioner, but it is still just an air conditioner. So that being said, where's my pointer? Let's move on. So one of the first things I want to talk about here is, and for those of you who were in the install training yesterday, we talked about this. We're going to talk about a little bit more today. One of the issues that comes up fairly regularly with mini splits is over or under controlling. Okay, so again, we need to know exactly how these operate to start to make sense of some of this. So one of the misconceptions is, and you'll hear it all the time, well, you know, we need a 12, but put an 18 in there. You can't oversize a mini split. That's not really true. Okay. It is possible to oversize a mini split. So I want to hit on some information, you know, that will help understand this. So this chart is from one of the Midea units, but it's the same as the Bryant preferred. And I'm looking here at this DHMS SHQ12. This is a 12,000 BTU high wall heat pump. Okay, and if I look down here, it says cooling capacity range, minimum and maximum. This thing has a maximum cooling capacity of 13,800. Okay, no problem. But it has a minimum of 4,000. So what that means is this unit cannot turn down below 4,000 BTUs. So it is possible to oversize them. I mean, they can't turn down indefinitely. So this 12 will turn down to 4,000. Now, if I jump up and say put a 2-ton, so if we come over to this 2-ton over here, you can see its minimum is 5,500. Okay, so again, you want to keep that in mind when we're sizing these things, or if somebody else sized them and we're working on temperature control problems. Now, if we jump down here to the heating side where this is more of an issue, I can see the same 12,000 has a turn down 5,000, and it'll put out as much as 15,500. So again, the 5,000 is as low as a single turn down. That's important to know. If I've got this unit in a fairly small area, and in the spring and fall, we seem to be overheating, this unit has a minimum runtime, and it only turns down so far. So that's important that we understand that. Now, if we look at the outdoor units, okay, that was the fan coils. Now we're going to look at these 38 MGR, which is the multi-zones. But we also have the numbers for the 1-to-1 condensing units. And I'm going to look at the 2.5 ton here, 38 MGR Q30. And the cooling capacity is 8,000. That's the minimum turn down cooling capacity in this unit. So what that means is if I have one 9,000 BTU fan coil running on this unit, it's the only thing running. I got more connected, but only that 9 is running. That 9,000 is getting 8,000 BTUs. Now, if I jump down to the heating capacity, you'll see the same thing. I have a minimum heating capacity of 6,300 BTUs. That's as low as a single turn down. Now, if I got 2 heads calling, that can be divided between them. But if only 1 head is calling, it's going to get that whole amount. So again, it's really important to understand this. Spring and fall, especially, we get these shoulder months where it's 50 degrees, 45 degrees, and you got a really small space with a large fan coil in it. And we understand that there is indeed a minimum these things can turn down. Okay, so hopefully that makes some sense. So what is Ductless we're going to talk about, and just a couple things. The single zone you'll refer to all the time. We have 1 condenser unit, 1 fan coil. On a single zone, I have 1 compressor, I have 1 set of lines, I have 1 fan coil. All right. Multi-zone, I'm going to have 1 condenser unit, but I'm still going to have only 1 compressor. Okay. So I'm going to have 1 compressor, but I don't have multiple fan coils. Now, and we talked about this yesterday, and you'll hear me say it all the time, but it still gets missed. On a multi-zone, I have to have at least 2 fan coils, okay? At least 2. So I cannot run these units with 1 fan coil, all right? And I still get guys, well, I want to do it. Well, you have to have at least 2. All right, but the multi-zone has 1 compressor. We have 1 condenser. We have 1 reversing valve. We have multiple expansion valves. But it's either going to be in heating or cooling. We can't do both at the same time. Again, that's something to understand, because we'll talk about some fault codes that pop up as we move on here. One called conflict of mode. So it's pretty important that we understand this unit can only do one or the other. You're going to see in a minute, right behind, if you see where my little laser cursor is there, that's our small line coming out. Now, you'll see that's insulated. Now, guys will refer to that as the liquid line. That is not a liquid line. That's actually a saturated vapor line or dual stage phase line, because the expansion valve is behind the sheet metal. So before it gets to that line, it's already been metered through the expansion valve. So both this line and the larger suction line are part of the evaporator. And the difference in temperature between these two would be your superheat. So if you think about the expansion valve, the superheat, and typically running full out, this thing, we're looking for about 9 degrees of superheat. So I get a lot of calls. Well, my liquid line is frosting. No, it's not. That's not your liquid line, okay? You will, for short periods of time, see frost on that line. That is totally normal. We're going to talk about the expansion valve in a minute, but the expansion valve on startup, they're all going to open up to like 250 pulses to unload the compressor, and then they'll start to throttle back. So for short periods of time to have frost on the small lines is very normal. Now, if I look here, you'll also see I only have a service port on the suction line, not on the saturated vapor line. And guys will always say, why don't I have a line on the other side or port? Because it's the same pressure. This from here to here is all the evaporator, okay? So that's why there's only one service port, because the pressures are the same on both, okay? All right, so the first thing we're going to talk about is the electronic expansion valve. So if I zoom in here, you can see this is inside the unit we just looked at. We took the sheet metal off and lined up. Lined up right here at the bottom, you can see the expansion valves. All right, so when you pull that front cover off, you see those little black rings. Those are the electronic expansion valves, or EXVs. Okay, so as we come out of the condenser, we go through our liquid line, we hit these expansion valves, we meter the refrigerant before it leaves the unit. So, this is no longer a liquid line leaving the unit. It's actually part of the evaporator because we've already metered. Okay, Right here, that is what the expansion valve looks like. Now that valve is two parts. It looks like a solenoid valve, but it is not. That black motor on the top is a motor. It's a stepper motor. This valve is 480 positions. So it's called a pulse motor. And so what happens is it can move 480 positions to fully open, 480 pulses to fully closed, and any place in between. Okay. Now, what it does, same thing as the TXV does, is it modulates refrigerant flow to maintain superheat. All right. You think about a TXV, it has a sensing bulb on it, right? Well, this has temperature sensors on the coil, but it's the same thing. We're measuring suction temperature, and we're going to modulate the valve accordingly. All right. Now, this valve, we're going to look at a cutaway in a minute, but you can see there's not, this is your liquid line that's leaving to go to the evaporator. Okay, so this is a cutaway picture of that valve. So you can see I actually have a needle right here, and it's actually threaded. And then this big black thing here, that's actually a magnet. And the motor magnetically grabs a hold of this and physically turns that valve in or out 480 pulses. Now this valve has been cut open just for to showing it what's inside, but this is actually totally sealed. That's stainless steel, it's totally sealed, so I can actually take the motor off this valve and not lose the charge. Okay, but that little needle right there, that's actually the goes into the valve seat, and that actually opens and closes and meters my refrigerant. All right, so what can go wrong with this valve? Well, it can get jammed up, it can get crud in it. This is why on mini splits it's so important that we do proper evacuations. We keep the lines clear. We run nitrogen in for brazing, because any of that crud can, booger up this this valve. Okay. So how could I check if this valve were working? Well, or if it's passing refrigerant. I can check temperature on one side of the valve to the other, right? Everybody should be going, yeah. I should have a temperature drop across this valve if this valve is open. What is it doing? It's taking liquid refrigerant. It's dropping the pressure and temperature to saturated refrigerant. So if this valve is metering refrigerant, there should be a temperature drop between the inlet and outlet. It should be measurable with a thermometer, and it should really be able to be felt with your hand. So it's pretty easy to determine if this is passing refrigerant. Now, could it pass refrigerant when it's not supposed to? Absolutely. Okay, like I said, what if we got something goobered up in here and it can't close all the way? Well, it's supposed to be closed, but we can check for temperature drop to see if it is or not. Okay, so the motor.
Hey, Dave.
Yeah.
Quick question on that.
Yeah.
Says, does each head connection have its own EEV, or just one for the whole unit?
No, on a single zone, there's only one, but on a multi-zone, if you look right here, this is a 2-zone 18,000, and you can see right next to the compressor there's two motors. There's one for each port. If this were a 3-zone, there'd be 3. If it's a 4-zone, there'd be 4. If it's a 5-zone, there'd be 5. So yes, every zone has its own expansion valve. And so this is how each zone can control separately by these electronic expansion valves. Okay, so yes, everyone. Now, if this for a single zone unit, one head, one condenser unit, there'd only be one valve, but they function completely the same way. And again, don't forget, this thing operates just like an electronic, just like a TXV. It modulates primarily on suction line temperature, but instead of a cap tube and bulb like we have on a TXV, we have a thermistor, temperature sensor. But they're pretty much functioning the same way. So now we're going to take a look at this motor here. Okay, the motor, which looks like this. Okay, that has like a quarter turn and slides on and off of that valve. All right, and it is a motor, it's not a solenoid coil. So I can pull the thing off, and you can actually feel it moving in your hand. You'll feel a vibration of the motor moving, but you can take it off without hurting it. It's not a solenoid, it's a motor. Okay, now there is a manual expansion valve magnet that you can get. Now, a lot of you probably have that CPS magnet for solenoid valves. That won't work. This is different because inside this, it's not a single magnet. It's a series of magnets. EXV, or electronic expansion valve magnet. There's a company called Carroll that makes one. It's about 50 bucks. I don't have a good source to bring it into BY. That's why I just tell you guys, you know, and for me to buy it from online and mark it up doesn't make any sense. But anyway, it's made by a company called Carroll, and it's a round donut looking magnet, but it's a series of magnets, and you drop it on top of this thing and you can manually open and close this valve. So if you do many mini splits, it's probably not a bad tool to have. Okay. We can check the valve easily enough. Do we have a temperature drop? Yes. We're passing refrigerant. We don't have a temperature drop. Okay, we're not passing refrigerant. We're not metering. Now the valve is either the wiring here, you can see it's either, in this case, 6 wires. Sometimes it's only 5 wires. Okay. Now, if you look on the right there, you'll see that plug and those little connectors there. These little connectors right here. The last thing you want to do is start cramming your jumbo meter leads into these connectors here. Because what you'll do is, see this one here is pushed down? It's damaged. So what you want to do is you want to get needle probes. Now, whatever meter you got, you carry, you can get needle probes for it. And then what we want to do is we're going to put the needle probe in the back of the plug, back here where the wires go in, for testing this motor. Now, how do I test a motor? Well, I'm going to pull it out. All right, so there's actually a couple different sets of windings. So you start by going, if you look here, lead wire color, red and blue. So I'm going to stick my probe in red and blue and measure my resistance. Red and yellow, brown and orange, brown and white. And they all should be about 50 ohms. Actually, they all should be about the same. It's like any motor. If I'm ohming out a compressor, same thing, right? If you ohm out a compressor, and if I have a short or no resistance at all, it's shorted, right? Okay, this is the motor, same thing. If it's open, the winding's open. Again, it's short. It's open now, so it's bad. So this is how we test that motor. Pretty simple. All right. Again, that manual opening magnet is kind of nice to have. But all right. So this is a 480 position valve. We ohm out the motor. There should be consistency, meaning all the windings should ohm out the same. We should have no shorts, and we can check at the ground that we don't have any grounds. Okay. One of the things on the motor, though, and this happened just the other day, actually, I just came across one of these. And when I pulled the head off the motor, there was a lot of corrosion on here. So one of the things you might want to do when you're having expansion valve problems, or even on the maintenance things, pull those motors off and clean these. Because don't forget, these condensate really bad, right? So I had a lot of corrosion built up on this thing. So just basically pop the motor off. You know, take your, when you look inside the motor, you'll see it's just a lineup of magnets. You can take a brush, clean those out, and then clean off the stainless steel piece here. And maybe that's part of just your maintenance. But if you have a valve problem, that's something you want to look at. Okay. Inverter. All right. This is the scary thing. Good old inverter. Now, I remember back when I started in this business a long time ago, back in 1980, we had mostly thermocouples still. And I remember the first job I ever went to, and there was electronic expansion or electronic ignition module. And wow, what do I do with this, right? I didn't have a clue. Well, all of us know now how to handle that, right? Because now we have integrated control boards in furnaces. But you check, I have input, I have no output, it's bad. That's simple. This is the same thing, same exact thing. So what we're going to talk about here for a minute is, what does this inverter do? Now, I'm not going to test you that you remember exactly what it does, but you know, some guys, this helps if they kind of understand what it's supposed to do. It makes sense and how we troubleshoot it. So if I look right here, here's my basic sine wave. If I look down in this box here, right? So basic 230 volt single phase sine wave. Okay, so what happens? I start at 0. I go up to 120 volt positive. I go back to 0, go to 120 volt negative, and then I do it all over again. Okay, and how many times do I do that in a second? 60. All right, 60 hertz. Okay, that's our power source. So we have 230 volts, 60 hertz. That's how it works. So what we're going to do, though, is we want to take this AC voltage and turn it into DC voltage. So what we're going to do is we want to chop the bottom of the sine wave off. How do I do that? Well, I'm going to go to a rectifier bridge. Again, you don't necessarily need to know exactly what this does. You just need to know how to troubleshoot it. So these are diodes. Okay. Now a diode is like a check valve. If you use a check valve in plumbing, we use my water heaters now and everything else. So it lets water go one direction, right? But water can't go back the other direction. So diode does the same thing. It allows power to go in one direction. It doesn't allow it to go the other direction. So when I go back to my sine wave, it allows the power to go to this direction. But when it reverses, it doesn't allow it to go this way. So that's how we cut that half the sine wave off. All right, simple, right? So we run it through the rectifier bridge. We chop the bottom half of the sine wave off. So now we only have this portion. But now, where these two phases drop off, we got this big old valley here, right? Now, so we add our capacitors in. If I look over here, I have 2, sometimes 3 capacitors. And what does a capacitor do? Even on a motor, capacitor takes a charge, and as the sine wave starts to fall off, the capacitor discharges to fill in these valleys. So it's exactly what happens. As our power falls off, the capacitors discharge, and we basically fill these little valleys in. Sorry, you're subject to my drawing on a computer, but I think you get the gist of this. So now what we've done is we've taken 230 AC voltage, and we've created DC voltage, a nice smooth DC voltage. How did we do it? Because we chopped half the sine wave off through these diodes, and then the capacitors discharge to fill in these valleys. Now, we all know these capacitors hold a charge. These are large capacitors. If you've worked on a mini split, you've seen them in there. If you're working on one of these things, those capacitors can hold a charge for 2 or 3 minutes. And we're talking about 300 and 330 volts. So before you go poking around in this unit, shut the thing down and wait for 2 or 3 minutes. Okay, you may have heard me sometimes. I'll talk, well, I cycle the power and it didn't clear. We'll shut it off and wait 2 or 3 minutes. We have to let this discharge first. But 300 volts will give you a heck of a poke. So you don't want to be poking your hands around in there. Until these capacitors discharge. So how can I test to see if this thing is working? That's actually quite easy. I have 230 volt AC coming in here, right? And I have about 300 volt DC coming out here. So I can go onto the unit, the power coming into that board, and I check for my 230 volt AC. Now I go on my board and I find my negative and positive terminals, and I check my DC voltage. It should be about 300 volts. How mini split, the most of the time the back of the board is looking up at you. You're looking at the solder terminals. And that's where you want to be, because all this is marked on the back. Now, sometimes it's hard to find the negative and positive terminals. But what do I see here? See these capacitors? They're between the negative and positive terminals. So on the back of the board, you can find where the capacitors are, because there's a circle, and there's 2 connections for a capacitor, just like all the other capacitors we use. So I can put my meter lead simply right there, and I should have my DC volts. AC coming in, DC coming out. If I don't, rectifier bridge is bad, which on most units, you change in the board. All right, pretty simple. So now I'm going to take this DC voltage, and guess what we're going to do? All right, so this is just a better look at the sine wave, AC volts to DC volts. I'm going to take the DC volts, I'm going to feed it into my, basically the inverter itself. I'm going to feed that DC power right in here. And guess what we're going to do? We're going to turn it back into AC voltage. Right, now, why did we do that? Well, because Edison sends us 60 hertz. And the phase of the power controls the speed of the motor. So what we're going to do is we're going to be able to change the hertz. So by changing to DC, recreating AC, now I can control the speed of the cycles. So instead of 60 hertz, I can drop it down to 20. I can take it all the way up to 150. That's how I'm going to control the motor. So I look here, I got W, U, and V, these terminals here. See them? V, U, and W. That's the compressor terminals. Those are polarity sensitive. So on the compressor, there's a terminal marked W. It has to be W on the inverter. There's a terminal marked U. It has to be tied to U on the inverter. And on V, same thing. So if you're changing compressor, you're changing inverter, make sure you get those wires back in the right location. Okay, really critical. So how do I test this thing? All right, well, this inverter actually has insulated gate bipolar transistors. Okay, it's a switch. All right, it opens and it closes. So what happens is we take the DC voltage in, these little transistors or switches open and close in milliseconds. And the faster they open and close, the higher the hertz gets, the slower the hertz are. And so these, by opening and closing, these little switches recreate an AC signal going to the compressor, but we can control the hertz. So here's my AC power coming in. Here's my DC power coming out. Again, look for the capacitors. I'm going to feed it into the inverter. And then I'm going to go through these transistors and recreate the sine wave and send it to the compressor on U, V, and W. So how do I test this? Well, I can check my AC power. I got DC power. All right, good. So I'm going to power this thing down. I'm going to wait for 5 minutes. You're going to wait for 5 minutes for those capacitors to discharge. Then I'm going to take my ohm meter. This is the back of the board here. And you can plainly see this circle here. That's the capacitor. Here's the other capacitor, and down here's the third capacitor. Here's my compressor terminal. U, V, and W, right? Pretty straightforward. We're going to let these capacitors discharge. I'm going to put my meter on mega ohm. So we don't need a mega ohm meter, just your regular meter. You're going to go, like you can see here, 20M, your mega ohm setting. You're going to put the red lead on positive, the black lead on U, V, and W, and you're going to get a resistance reading. Then you're going to take the red lead and move it to negative, and you're going to do it again. Okay, and we should get 6 readings, and they should all be consistent. This is straight out of the service manual, but I wanted to show you how this works. And we'll talk about this again as we move on, but it's pretty simple. So this is the back of the board. How do I check for that DC voltage? Well, again, here's the capacitor connections. There's one, there's the other. So there's positive, there's negative. So I can check for my DC volts right there. And it will be around 300. It might be 320, 329. It might be 195, but somewhere around 300 volts. If you don't have it, then you know the bridge rectifier is bad. And again, on all but 2 units, that rectifier bridge is part of the main control board. Okay, then we can check our transistors or our switches. Now, last but not least, what I can do is I can check the power coming out of these terminals here. So when the compressor is calling, I can actually check for power going to the compressor to see what it is. Now, it might not be 230. It might be 190, it might be 150, but it should be the same. So here's just a kind of common breakdown on how the rest of these controls work. So there's my 230 volts, 220 they say here. We go through a filter circuit. There's that rectifier bridge. That's where we take AC and convert DC. Then we're going to go through some more filters. Then we're going to go through inverter module, which feeds the compressor. All right, AC, DC, AC, but we control the sine wave. All right. Now, On the smaller units, this is on one board. On the bigger units, this is two boards. This bottom portion is our controls or our main board. So there, we're going to take 220. We're going to create AC to DC voltage. We're going to drop it down, and then all of our control circuits in DC as well. So 3.3 volts, 15 volts, 12 volts. Okay, so again, on these, it's just as easy. We're checking for AC volts in, and then we're going to check on the board to see if I have my DC volts. And a telltale sign is look for blinking lights. So we'll talk about that as we move on. All right, so again, on the bigger units, this is two boards. On the smaller units, this is one board. The inverter and the control. Okay, so if I look at this, this is what it kind of looks like. So here's my main board. If I look down here, here's my L1 and L2 coming in, right? They feed the main board. Then the main board takes that up here, it comes off the main board and it goes to the inverter board. Okay, that's where we take our AC, convert to DC, and then there goes to the compressor. Okay, this particular unit now, this DC voltage we created here also goes back to the main board. Okay, but, all right, so that's all pretty simple. Here's those expansion valves we talked about over here. See valve A, valve B, valve C. Okay. All right. So we have our inverter that controls our compressor speed. We have our modulating valves. Now we're going to look at this guy right here. Return air thermistor. Okay, that is your control thermistor. Now I always get guys call and say, well, I got a wired thermostat. No, you don't. You have a wired remote control. All right, big difference. Thermostat has a temperature sensor. These remotes do not. That is the operational thermistor right there. All right, so wrap your brain around that, because if this thing is 7 feet in the air or 8 feet in the air, 9 feet in the air, it's controlling to that up there. All right, and you're checking temperature across the room. Yeah, they're not going to be exactly the same because you're measuring temperature way over here. Okay, it's just a thermistor. We're going to use an ohm meter. Generally on thermistors, if they're shorted, they're bad. If they're open, they're bad. If you're getting a reading, they're normally good. I used to always say that, and about 6 months ago, I did run into one that the sensor was reading off. A unit that wouldn't run, had no faults, and it didn't make any sense. It wasn't even calling. So we, went back to basics, right? Start checking all the simple things. We go through all the thermistors, and my outdoor air thermistor was reading 154 degrees. So the unit wouldn't run. Okay, so there is my return air thermistor, or my main control thermistor. This is, like I said, when you set to 72 degrees, this is main thermistor that is controlling 72 degrees. Okay. Then we have a coil thermistor. So this picture right here is on the, you can see the U-bends here. That's on the end of the evaporator on the indoor unit. And then you see the well here brazed on, and then there's your coil thermistor. Okay. That little guy on a single zone is what controls the expansion valve. Okay, now on a multi-zone, we have it does as well, but we also have another thermistor that does it. So there is my coil thermistor. Again, that helps modulate the expansion valve, but also that keeps that coil from frosting. Now, if you call and say, hey, Dave, my coil is frosting, I'm going to tell you have wires crossed almost 99% of the time. Why? Because this little thermistor here will keep that coil from frosting otherwise. Okay. So what happens is if you have a multi-zone system and you got the wiring crossed between zone A and zone B, and zone B is calling, we're sending refrigerant to zone A. Well, zone A is not on, so this sensor can't help. And so that coil will frost up. So, all right, so that's our second sensor. Okay. Now, multi-zone. This is only on the multi-zones. So behind this metal plate here, you have your expansion valves here, but on the suction lines, we also have sensors on every one of those suction lines. Okay, that's the T2B sensors. So this is only in the multi-zones. Okay, and on the multi-zones, this is what controls the expansion valves for each head. Okay. All right, and again, we're just going to use an ohm meter for checking those. Now over here, this is on the back side of the unit, on the outside unit. There's your condenser coil. That's the ambient sensor. Now, if we were in a classroom, I'd say, hey, what does he think the ambient sensor does? And somebody would yell out, it's for low ambient control. Yes, it is. So that little guy is primarily for low ambient control. Okay. Now, if we look up here, same thing. Here's my thermistors, my T3, that's the ambient, T4, which is condenser temperature. But to test these, get some needle leads. Please, please, please don't use those big honking leads that came with your meter. Get some needle leads and push them in the same place where the wires go in. Do not put them into the face of that plug. You're going to destroy those connectors. And you just created a problem that didn't exist. Also, when you see in the wiring diagram and you see this little block here with 2 arrows, that indicates a plug. So like here, that indicates that this inline plug is there. So what does that matter? Well, that means I don't have to get up to the board, which is upside down. I can actually unplug and test it from here. Okay, so there's the outdoor air thermistor. Tucked way back in here. It's hard to see. But way back in here, this is a condensing unit. You can see the U-bends back there. And that's where the outdoor coil temperature sensor is. All right, it's way back in there. All right, that is, oh, I changed slides here. Okay, it's way back in there. That's the condenser coil temperature. All right, that's what controls defrost. So when we start talking about defrost, that sensor controls defrost. So if we have defrost issues, we want to look at that sensor. Okay. And then last but not least, we have the compressor discharge sensor. So right there, you see it strapped on the compressor discharge line. Okay. What does that little guy do? Okay, it protects the compressor. That's what it does. All right. What cools the compressor? What cools the motor in the compressor? Suction gas, right? Everybody should be saying that. Not, oh, you know, obviously I can't hear you, but you should be saying it yourself. Suction gas. Right. So if my suction gas is too warm, what happens to my compressor discharge temperature? It goes up as well. So for instance, let's say we're low on refrigerant. And if I'm not cooling the compressor starts to heat up. What happens to a regular compressor? We end up burning it up. What happens to this compressor? It goes, ooh, my discharge is getting too high. It's over 200 degrees. Start slowing the compressor down. So.
Hey, Dave.
Yeah.
Quick question.
Yes.
Someone asked, he said, can we get a printout of with all the resistance values?
Yes, it is in the service manual. All right, we'll talk about the service manuals a little bit later, but all those, there's only 2 thermistors they use. All of except this one have one set of values, and then the compressor discharge has a second set of values. But we'll talk about that as we get into the service manuals, where to find that.
Thank you.
So now this, and this is important to know because this is what's going to throw guys. This always throws guys. Well, they tell me, well, I put my gauge on there. My suction pressure was normal. It can't be low on charge. What this little guy does is we're low on charge. The compressor discharge starts to climb. It slows the compressor down. So if the compressor's pumping slower, what happens to my suction pressure? We're not pumping refrigerant as fast, so my suction pressure goes up. So I could be grossly undercharged and show normal suction pressure. Okay. So let that sink in for a second. I can be grossly undercharged and have normal suction pressure. because the compressor is protecting itself, so it's slowed down. So it's not pumping as much. So you can actually add refrigerant and watch your suction pressure go down. Okay, now that seems odd, but you add refrigerant, discharge starts to fall, compressor speeds back up, suction pressure goes down. This is a big reason right here. It's not the only one, but this is a big reason right here. Don't put gauges on this thing unless you're removing refrigerant, you're evacuating, charging, because that pressure means nothing to anybody. Don't call me and say, my suction pressure is this okay? I don't know, because this is a modulating system. Okay, so there's our thermistor for our compressor discharge. There's the chart you were asking about right there. Okay, so this is, so the discharge temperature sensor, the one we just looked at. Okay, this is it. So at a given temperature, you have a given resistance. So at 72 degrees Fahrenheit, it's 62,000 ohms. All right, pretty straightforward. So I can simply measure my resistance, look on the chart, and see if the temperature is correct. Now, the exciting news is there's a way to test these without using a meter, and we'll get into that later on today. But these charts are right out of the service manual, and there's only two different thermistors readings or ranges they used. The first four we talked about, and then the discharge temperature. So again, if you're not familiar with a thermistor, it's a resistor whose resistance changes with temperature change. So if you look down this chart here, at 70 degrees, it's 65,000 ohms. At 62,000 ohms, that's 72 degrees. So as the resistance changes, that's indicating a temperature change. So the board's calibrated to know at what resistance, what temperature we're reading. Pretty simple. They're generally good or bad. So if you have some resistance, normally they're good. If they're open or shorted, they're bad. But the unit's going to tell you when they're bad. Okay. So we're going to look at the remote for a minute. Now, there's some features on this remote that we're going to use. And if you're talking to me on the phone, you may hear me ask you to use this feature. So we're going to talk about a few of these here for a second. But here's the remote, very simple. There's no hidden door, no special, bunch of buttons. Most of these are very self-explanatory. The LED button I want to point out. So right here, I have the LED button. This little display, I've seen this more times than not. I'll go into a house to help on a job site visit, and the homeowner's got a piece of duct tape or a Post-it note over that little display. Because the display is too bright in the bedroom at night. You can simply hit that LED button, that display will go out. All right. Now, if I want the homeowner to play with that button, they won't. But when you don't want them to, they would. So, but just know that's there, because so many times I'll show somebody, oh, that's awesome, I can shut that off. All right. This is the set point. This is not temperature. This is set point. So this unit's set at 72. Okay. Turbo mode. There's a turbo button here. Now, one of the things I'll tell you to do, you'll be, calling me and, well, I got no fault codes, but we're trying to check operation. We're going to take the temperature way up or way down. So in heating, to test it, I'm going to crank it up as far as it'll go. In cooling, I'm going to crank it down as far as it'll go. I have to get way off set point. And I'm going to hit turbo. Okay. What a turbo is going to do is it's going to increase fan speed for 30 minutes and crank this thing up to a higher capacity. So during our testing, we're going to do this turbo. After 30 minutes, it'll go back to normal. Follow me feature. Now, follow me. Remember, the first sensor we looked at was return air sensor. There is a sensor in this remote. So if I've got a temperature control problem, I can go to follow me, which I push the follow me button, a little person will pop up on the screen. Now this unit's going to run to the sensor in this remote. All right, so wherever I put this remote, it's going to partially read to this. Now, I want to make this really crystal clear. It did not take the return air sensor completely out of the equation. This is kind of resetting the return air sensor. So if that return air sensor is in a really bad spot, follow me is not totally going to cure it. Okay, and we'll talk a little bit more about that in a minute. Also, and follow me, if you look down here, the last bullet point, 2 degrees Celsius offset. So if I set this at 72, it'll go 1 degree above 72, 1 degree below 72 Celsius. Okay, now, what does that mean? Well, 2 degrees Celsius is about 3.6 degrees Fahrenheit. All right, so what that means is I have basically a 4 degree dead band when we're in follow me. So if I'm set at 70, it can go all the way to 72 and all the way down to 68. Most cases that's fine, but again, temperature control issues are a big thing that happens with these. So when we're using follow me, we need to understand how it works. Okay. Also, follow me needs to, if we go into follow me, this remote needs to stay in visual contact of the unit. These are infrared remotes, just like your TV remote. So it has to have visual contact with the unit or it will disconnect. So just again, remember that. Okay. Emergency mode. All right. This is also a great feature for troubleshooting. However, if Mr. Homeowner finds that it can cause other issues too. What this does is if we lose one of those thermistors we just talked about, right? Say one of those thermistors goes bad and we get a fault code, and I think it's like an E4, E5, telling us the thermistor's bad, right? And you get out to the job and you find, okay, the coil thermistor's bad. And, you know, what the heck, it's Thursday evening and you're not gonna be able to get back with the part till tomorrow. I can put this unit in a forced operation mode, even though I have a sensor failed, or an emergency mode. So each fan coil, every single one of them, this is the mid-tier high wall, there's this little opening here and it will say manual, and you stick a paper clip down in there and you push a button one time and it puts this thing in a forced auto mode. So we look here, forced auto mode with the set point of 75 degrees. So forced auto, meaning it'll heat or cool, whatever it needs to maintain 75 degrees. So at least it'll do something until we can get back with that thermistor. Okay, so press it once, it's forced auto at 75 degrees. Press it a second time within 5 seconds, 30 minutes at forced cooling, and then it would go in forced auto. Press it a third time, it takes it back out. Okay, so know that little guy is there. Another time where that's useful, if you're wondering whether or not the remote is working, right? Because the remote doesn't seem to be functioning. So is the problem the remote or is the problem the fan coil? So I can manually turn the fan coil on with that button. Now, on the floor consoles, it's right on the front. So it's a little more likely the homeowner might bump it. So the way to know for sure we're not in that mode is just kill power to the unit for a minute and turn it back on. All right, but they'll know that that's there, and that's on every one of them. Again, another great troubleshooting feature. The timer function on the non-programmable remote. Again, this is when we'll get calls on. Somebody uses, this is the wired remote, the non-programmable wired remote. But there's a timer function on here. So we got time off, time on. Sounds like setback, doesn't it? No, what that does, the time off mode at 10 o'clock, it shuts the unit off and it turns it back on at whatever time we set it to turn back on. So the non-programmable has this time function that shuts the system down. Now that's another one I've run into. Customer doesn't understand that, so they set a timer and the unit shuts off. Well, how do I know? Well, the little red light is off on the unit. Well, the only way that could happen is somebody presses that little power button here, or we set a timer. Okay, so, okay. Connecting the wired remotes, the 5-wire non-programmable plugs into a harness, and then there's also the programmable that plugs directly into the board. Okay, so I'll get that call while you're trying to install one of these things. Now, if I look at this, okay, this is actually the setback stat, but this remote also has a timer function on it, and it also has the follow me function on it. So even if I'm using this remote right here or the other one, we're still running on a return air sensor. Okay, this is a remote, it's not a thermostat. Now, I can put it in follow me, just like the wireless. We still have that 2 degrees Celsius dead band, and that return air sensor still in the equation. We didn't take it out.
Hey, Dave.
Okay. Yeah.
Dave, we got a quick question. It says, in emergency mode, is the set point based off the remote temp?
No. In emergency mode, it's set at 75 degrees. So if it gets above 75, the air will come on. If it gets below 75, the cooling's going to come, or the heat's going to come on. So that's not adjustable. It's just set at 75. But it's better than nothing, right? I mean, it's hot. It's you know, it's the weekend. It's Friday, and it's their bonus room. Now it's going to run cooling at 75 degrees instead of being 85. So, okay, so there is no set point in emergency mode. It's emergency auto at 75 degrees. Okay. Remote compatibility. Okay, again, this is another thing we get calls on is, hey, I had a wall unit, and the homeowner wanted to add a wired remote. Well, I had a one in my truck. I put it on there and it fried. Okay, so if I look here, here's the high wall units. Okay, there's all of them, high tier, mid tier, low tier. They use this remote here, this 401. If you look down here, the cassette, the ducted and a floor console use this one over here, which is the 501. One is 10 volt DC, one is 5 volt DC. So be aware that they're different, okay? So don't just pop, hey, I got this left over from a previous job, we'll slap this on there. Yeah, maybe you won't. 24 volt interface. If you know, this is available for any of these fan coils, and it wires in between the indoor and outdoor unit, and it adds a standard thermostat. Now, one of the challenges with these things we've already talked about is we run on return air sensors, right? The unit is on one side of a 15-foot long room and running on a return air sensor, and 15 feet away, where Mrs. Jones is taking a temperature with her $2 thermometer she bought at Walmart, it's instead of 72 it's set, it's 65. All right, and you know, you try to explain to people, hey, temperatures are always different in the room. Everywhere in the room, you have different temperatures. But occasionally you get that person that absolutely wants that traditional style operation, right? Got a thermostat set point temperature. And so this interface allows us to use a standard 5-wire thermostat. Okay, so know that that's available. Okay. Heating mode. On a multi-zone, again, this is all important stuff in understanding how these things work and why things do what they do. In heating mode, okay, or in a multi-zone rather, the heat mode is always the priority. Okay, so if I put them all in auto mode on a multi-zone, all right, if there's a heat call, it's going to handle the heat call first. Then it will take care of the cooling call. Now we have a minimum runtime of 3 minutes. We have minimum off time of 5 minutes. So what happens is, okay, we got 2 units, one's in heating, or they're both in auto. One's calling for heat, one's calling for cold. Well, the one needs heat, it's going to heat. Once that heating call is done, now the unit's going to shut off. It's got to stay off for 5 minutes. It's going to switch over to cooling. So it's going to come on in cooling. Now it has to run for at least 3 minutes once it starts. Now, 8-9 minutes have elapsed at this point. So by the time the cooling starts, the heating call comes back. So we got to switch back over to heating to take the heating call. So why I bring this up? Because again, one of our challenges is these sometimes get misapplied. The example I always use is I had a grow room, guy had a barn with 2 grow rooms, which always need air conditioning. His office was on the same multi-zone, which needed heating. So what would happen is the changeover with all these timeouts is you could be 14, 15 minutes before you do change, before the changeover happens. So as soon as his office was satisfied, by the time we got the cooling started in the grow rooms, we'd be switching back over to heating again. So just know that's how these work. Heating is a priority. I cannot change it. And with all our time delays, these units are not designed to operate flipping back and forth like that. Okay, these are designed to be heating or cooling. If we've got really large differences of load like that, where you have a grow rooms needs cooling all the time, an office that's going to need heating sometimes, those should not be on the same unit. Okay, that's a misapplication, but we come across them. All right. So again, to understand how that works. Second bullet point here, when one zone is in heating on a multi-zone. So remember, we looked at those expansion valves. We could have 2 or we could have 5 on a multi-zone. If zone A is calling for heating, all the other zones are open about 15 pulses just to keep the units from oil logging. So again, that's important to know, because as I walk by this coil, it's a little warm to the touch, but it's not calling. Is there a problem with that valve? All right. So again, put that one in your memory. If one zone is calling for heating, all the valves are open slightly. It's not the case in cooling, but in heating it is. So again, what can happen if I got a really small space, spring and fall, I got a 9,000 in a little bitty closet basically, and one of the other units on the system is calling, that little bit of heat trickling through that unit on a 45-degree day may be enough to overheat that space. So again, it's important we understand how these things operate. Okay, last but not least, heating operation will not happen after or above 86 degrees outside. So one of the things we like to do is run both modes, heating and cooling, to test them. But if it's above 86 outside, we can't. All right, so everybody clear on these two top bullet points? Okay, because it's really kind of important, because again, heating control or set point sometimes is a big issue. And a lot, we have to understand how all this works. Okay, defrost. How does a heat pump defrost? For those of us who aren't real familiar with heat pumps, our reversing valve de-energizes, and we return the system to air conditioning for a minute or for a few minutes. So what happens on a call for defrost? Indoor fans shut off. The reversing valve de-energizes. We go back into cooling for a period of time. So the outdoor coil becomes a condenser again. We heat the coil, melt the ice, and when the coil temperature gets high enough, we'll terminate defrost. Okay, so this is in the demand defrost. Defrost will happen on a couple things. Runtime. We have to have accumulated runtime of so long. I believe it's like 10 minutes, and our coil temperature has to get below a certain temperature before we'll go into, defrost. So it might defrost once a day. It may defrost every 2 hours. It just depends on outdoor ambient and how much runtime. All right. So defrost, there's no forced defrost other than putting it back in cooling for a short period of time. Okay. So, all right, it's 10:05, so we're going to take our break. I'm running a little bit long here. This class is going to run a little long. I know it says 2 hours, but we're going to be a little bit beyond the 2 hours. So, so before I start losing people, because sitting for an hour looking at your computer screen, listening to me ramble on is not always easy. So let's take a 10-minute break. It's 10:05 right now. Let's be back at 10:15. Okay. So we'll be back at 10. See you. All right, we're gonna get started again. I feel like we should have some type of music playing when we restart, kind of like coming back from commercial. I amuse myself, so. Um, okay. So we talked about the basic operation, the basic components, okay? We talked about some of like some of the remote issues and things like that. Now I want to get into error codes. Now, the first thing we got to look at when we get a call on a unit, is there a fault code or is there not? Because if there's a fault code, the unit thinks everything's fine. So it's at that point, it's usually a basic air conditioning problem, low on charge, control issues, things like that. Nothing wrong with the unit. Changing the inverter board is not going to fix it. So we're going to look at the error codes. All right, what and where to find the error codes. Now, I'm going to caution you guys. Depending on where you recover the error code from is going to dictate what service manual you need to go to. Okay? Really, really, really important we look in the right spot. All right. If you have a wired remote and we get a fault code, we need to look in the book for the 24 volt or for the wired remote. If you have a 24 volt interface, you need to look there. If you get the fault code on the indoor unit, you need to look there and so on. So again, is if this remote, if your code pops up on the face of this wired remote, we need to look in the book for that remote. Not in the outdoor unit book, not in the indoor unit book. We need to look in the book for that remote. Okay. If you look in the wrong spot, you might be chasing the wrong fault code and do a bunch of work that didn't need to be done. Okay, so here is the troubleshooting list for the wired remote. So if I look right here, where'd we go here? We can see it says wired remote controller display. So I look down here and let's say for instance, I got this E8. Now if I look in the book for the indoor unit, E8 is a whole different thing. See? All right, so make sure we're looking in the right book. So if I get a fault code on the indoor unit. So first of all, on the high wall unit, the fault code will show up right here. On the ducted unit, the fault code will show up right here. Okay, if on the ducted unit, you're using the wired remote and your installer failed to leave this little fella behind, you can't troubleshoot it. All right, so just remember that if I'm doing a ducted unit and I'm doing a wired remote, leave this guy behind. You see it shipped inside the control box right here. All right, because I can't troubleshoot without it. So again, the high wall and the ducted unit has a digital readout. Okay, the ceiling set and floor console are just flashing lights. So on the floor console or the ceiling cassette, you can see right here, this little window is actually infrared receiver, no digital display, but there's lights right here. Okay, so, and then on the floor console, there's lights, blinking lights right there. Right. So if I have blinking lights, I have a fault code. If I have no blinking lights, I do not have a fault code. Okay. Even on the high wall and the ducted, the flashing lights are there too, but we get a digital readout. But if you get called out on one of these things because it's not working right, and I don't have a fault code on these two or blinking lights on these two, the unit is not faulted out. All right, so the unit thinks everything is fine. That means the sensors are good, the compressor is good, the inverter is good, fan motors are good. All the hardware is good if I do not have a fault code. So now we got to start looking at a traditional air conditioning issue. If I am getting the blinking light, then I got to recover the fault code and look in the book. So this is on the outdoor units. So the outdoor units, 1-to-1, meaning one fan coil, one condenser unit. And I have these two blinking, these LEDs right here. Okay. Those are going to give me a fault code. Now in a 1-to-1, this code and the code here will be the same. So on the one-to-ones, I can pretty much just go by the code for the indoor unit. But I do have a code on the one-to-ones as well. Okay, so this is a 9 through 18, 24 to 36. And actually these lights are behind the inverter heat sink right back there. Okay, and this is how they translate. So normal standby. So on a one-to-one, the lights on the board on the outdoor unit, it's meaning everything's normal, but it's not running. LED 3 should be on, LED 2 should be off. So again, this LED should be on, this one should be off. Okay, now what do you think powers those LEDs? Remember the old rectifier bridge that takes AC voltage and creates DC voltage? That's what powers those little guys. So if those little lights are on, guess what? The rectifier bridge is good. If those little lights are off, it's a good possibility that we lost that rectifier bridge. Okay, that's a simple way to know that I have my DC voltage. Okay, so here's the fault codes for that. Normal, standby, DC voltage is too high. Now, every one of you knows how to troubleshoot that now. You don't even know it, do you? What if the AC voltage is too high? Where did the AC voltage come from? Or the DC voltage, rather. If the DC voltage is too high, that means the AC voltage is too high. Because remember, we took the DC voltage, or the AC voltage, rather. We cut the sine wave in half and created DC volts. So if the DC volts is too high, because the incoming AC power is too high. All right, so that's not an equipment problem. EEPROM error, that's the board problem. Compressor speed malfunction, most of these are pretty self-explanatory. IGBT, that's the inverter itself. Remember the transistors, current protection, meaning the compressor's overamping. So anyways, these are the codes for the single zone outdoor condenser unit lights. Okay, multi-zone outdoor units. So on the 2 and 3 zone, which is the 18 and 24,000, if you look right here between those two wires, you see a digital display. There's a 2-digit display in all the multi-zone units. And I can also get a fault code in that unit right there. Okay. In the 2.5 ton, it's right here. And then in the 3 and 4 ton, when you take the front cover off, it's looking at you in the face right here. Okay. There's also a little push button right here on the multi-zones. And I can use this little push button to look at a lot of different information on this display here. Okay, so if you get the fault code on the indoor unit, make sure you look under the indoor unit. All right, this one happens all the time. I'm working on a multi-zone. I got a P6, right? Now look down this list. Do you see a P6 anywhere on this list? No. All right. Oh, there's a P6 over here though. That's under outdoor units. Everybody see that? So I can't find I get a P6 on the indoor fan coil, right? Right here, I get a P6 pop-up, right? So I go to the troubleshooting guide. I look, there's no P6. Huh. Oh, over in the outdoor unit, there's a P6 over here. Oh, inverter, IPM module, inverter power module. Remember, that's the scary part, so we changed that because it says IPM module must be bad. You change it, Matt, it didn't work. I'm still getting a P6 on the indoor fan coils. All right, this is because there is no P6 in the indoor fan coils. So I have to go to the outdoor unit. Remember on the multi-zone, I said they all have this digital display. I need to see the fault code here. So in the case where they've got a P6, they changed the inverter because they looked here. I told them go to the outdoor unit and check, and they got a P1, which is high pressure switch. Now, I'm assuming we all are air conditioning technicians, right? What makes a high pressure switch trip? Air conditioner, guys, you know that one. Okay, fan's bad, condenser's dirty, the switch failed. Okay, so again, I can't stress enough, wherever you get the fault code from, make sure you look in the right book for it. And if you're doing a multi-zone, check the fan coil and the outdoor unit, okay? So hopefully that all makes sense because we got to look in the right place. Okay. All right, and we'll look at some of these more common or some of the more in-depth ones as we move on here. But let me change my pointer up again, back to my laser. But some of these are pretty easy. Okay. F1, A indoor unit coil output sensor is faulty. B, sensor's faulty. So if I have a bad sensor, it's just going to tell me the sensor failed. High pressure switch, low pressure switch, those are pretty easy. Current protection of the compressor means the compressor is drawing too much amperage. Well, again, this is an air conditioner. What causes a compressor to draw too much amperage? Compressor discharge protection. That means the compressor discharge got too high. So most of these are really, really pretty straightforward. Get into the manual, see what the problem is. Outdoor fan speed has been out of control. Well, if the fan's not running the right speed, what do we check? Well, is something hitting it? Does it spin freely? Is there ice hitting it? Or the fan motor's bad? Okay. Here's the other sensor up here, the T4. It's all pretty straightforward. Some of the big ones, and we'll talk about these, are communication error and then inverter error. All right, some of those are some of the common ones are a little harder to deal with. But most of these, look at the thing, and then you go to the troubleshooting guide, and it'll tell you exactly what to look for. Okay. All right, so we get called out to the job, and again, we're going to refer back to the troubleshooting a little bit later, but we're going to come back to other issues. So customer calls, says we're not controlling correctly. And you get there, there's no blinking lights, there's no fault codes. That means everything hardware-wise is normal. Okay, so we got to kind of get that in our heads. Sometimes this is a hard one to get by. Well, it's not controlling right. Maybe the board's bad. No, it's not the board. If it's not controlling right, there's most likely a reason why it's not controlling right. So that's some of the things we're going to look at. Okay. These clearances, and again, for you guys who were here during install yesterday, we talked about this as well. But if these are not located in the right place, if we don't follow these clearances, we are going to create control problems, which have nothing to do with the equipment. But a big chunk of the calls we get have to do with installation issues causing control problems. All right. And everybody wants to start faulting, changing boards, changing sensors. We got to go back to basics. How is it installed? So we don't follow clearances. I had one right where we had high wall units, and they're up on top of walk-in coolers in the store. And I'm supposed to have 6 feet below the unit. I didn't. And so what happens is that cold air comes out, or the hot air, whichever, hits the top of that cooler, recirculates right into that return air sensor, and it shuts off. And they're yelling, equipment's horrible. No, the equipment's fine. We didn't follow directions. So how do we fix it? Well, I have to move. Well, I can't move the cooler, so I have to move these units. Well, who's going to pay for that? Well, I didn't put them there. And the instructions clearly state. So if you got control issues, and which is a big call we get on these things, we got to look at the installation, all right, and start using some common sense. This one here, return air sensor is right inside right there. Remember, we looked at that first sensor picture. If I set this at 72 degrees, it's going to control the 72 degrees right up there. Is it 72 degrees down here at that chair? No, because that's 9 feet in the air. 68 down here. That right there explains why that is not heating to 72 degrees down here, because it's sensing up here. Hopefully that makes some sense. So 9 feet in the air is probably not the best place to put this. Should have been maybe down here at 7. Okay, how can I correct this right here? What's the best way to correct this? Well, I could use follow me. and have Mrs. Smith hold, put the remote down here on this little shelf. That's going to make it better. But remember, follow me doesn't completely eliminate the sensor. 24-volt interface would be a good option for this. Put a standard wall thermostat, put it over here on the wall and make it run like a traditional system. Okay. So we don't want that unit too far in the air on a high wall because of where it's going to control. And again, this is where you have to start wrapping your brain around how this thing functions. So the thing I would do is, first of all, get a temperature probe right here. And chances are you're going to find whatever this is set at is what you're reading right here. So that means the unit's working perfectly. So we have to look at some other solution. All right, this application right here. Number one, the instruction manual clearly says, do not put it over a doorway. All right, do not put anything underneath it. This is going to hit this, it's going to recirculate. We're going to do one of these. We're not going to control right. How do I pinpoint this? Get a temperature probe up in here on your sensor or read the sensor and see what the set point is. And chances are, if this is set at 72, we're reading over 72 up here. All right. This application here, this was a call I got. This is a beautiful installation, did a great job. Now, if you look back over here, here's the kitchen. This is the living room area. And in that little circle there is where the return air sensor is. So if I set that at 72 over in that kitchen area by the table, is it going to be 72 over here? No. Could be 68 over here. A lot of jobs, that's okay. Okay, as long as the homeowner understands how this works. So this is nothing wrong with this installation, but we have to, again, understand how these things work. If I put a wired remote control right here, is that going to change it? No, because I'm still sensing from over here. If I put it in follow me, is that going to fix it? It'll make it better because now we're sensing from here, but we're still sensing from over here as well. Again, one of the ways we could fix something like this is the 24-volt interface and make it a more traditional system. But this is stuff we got to get used to looking at. We think of troubleshooting as inverters and compressors, but a big chunk of it is this stuff, all right? Understanding how it works and looking at this job saying, okay, you know what? It's not going to be the same temperature here as it is over here. We're in two different rooms, right? All the heat's over here. If I put a register over here and had no registers in this room, the temperature is going to be different, right? It's just how it works. All right, this job here. Anybody see any issues here? First of all, my return air sensor is right there. You see this diffuser here? I have a makeup air unit right here. Okay. Do we see any problems with that? Sure, that makeup air unit could be dumping right down on that sensor. All right. What about this? Has anybody ever been in a commercial kitchen with the dishwasher running? I used to work at a smorgasbord, and we had one of these big Hobart dishwashers like this, and man, there'd be a cloud of steam just pouring out of this thing. Well, steam is humidity, is it not? Latent load. And these units actually have a maximum design condition for humidity, like 80%. So what happens is the humidity is so high, this thing is sweating so bad. You see this big PVC pipe they put here for the drain? All right. And you'll actually get fog coming off this unit because the humidity is so high. So again, part of what we do in troubleshooting these things is look at the install. Right? Is the install causing the problem? In the case in this one, we kept losing boards in this unit. Why? Because we had so darn much moisture in there all the time, and electronics don't like water. All right, so again, not a great location for that head in this dishwasher room. Okay, condensate handling. Again, these units have a built-in lift pump, but there's a limit on how high they can lift. So something we need to pay attention to. If we're not getting rid of the condensate water. If it's dripping, did we do this right? Did we pump this too high? Some of these, it's only 21 inches. All right. So again, that's something we're going to run into. Ductwork on a ducted unit. All right. Again, I have no fault codes, but I have control problems. Well, you always get the question, and as a guy who did service for a lot of years, you know, back in my day, we still had the old incline manometer that you had to put the red oil in it, and it was dumped all over your truck every time you needed to use it. And nowadays, you got all this electronic stuff, which is great. But static pressure is a big thing. Now, guys always, branches even call me, hey, I'm going to put a 2-ton ducted unit in. How much ductwork can I put on it? I don't know. You have 0.2 inches of static available. Okay. You don't need to be a duct whiz to understand I got more than 2 inches of static here. Of course, this is just a picture I found on the internet, but you get the point. But these units come out of the box set for 0.1 inch of static. We have to set the static. Guess what the installer didn't do? He didn't set the static. So if I didn't set the static, I'm not getting enough airflow. All right, and we all understand how airflow and air conditioning go hand in hand, right? Okay, so again, no fault codes, but I'm not controlling properly. Well, because the installer never set the static. All right. Well, we don't know what he designed it to, so how do I set it? Well, if I look here, I have an automatic airflow adjustment. So I simply take the wired remote that came with it. If they're not using it, I simply plug it in. I go to the airflow adjustment, automatic. I put it in that adjustment, and the unit will run for 5 or 6 minutes and set the static itself. All right, so it'll adjust itself. But again, that's going to come up in a troubleshooting situation a lot. Okay, again, the ducted units, the fault codes come up on the display. This is also the receiver for the infrared. So if the installer took this with him, we can't troubleshoot this thing. Okay, so if you're installing one of these and you're using the wired remote, leave this behind. Okay, it's shipped inside the control box like you see it. All right, you might move it to the outside of the control box so you can see these lights. There's that manual button right there. Okay. Remember on this one, return air sensors right there. All right, so if I've got 72-degree return air coming from the space, and I got leaky ductwork, so 72 coming up here, but I got leaks all along, and by the time the air gets here, it's 62. Can I control properly? You know, it's 20 degrees in that attic. So if my 70-degree return air becomes 62-degree return air by the time I get to the return air sensor, what am I going to do? I'm going to overheat. All right? I'm going to overheat. Okay, and you're going to get that call, especially in ducted units. And I'll tell you, if you look at this, part of the problem is this air handler is not insulated. This ductwork needs to be sealed, and this air handler needs to be insulated. And it's simple again, stick a temperature probe in here and read what the sensor's reading. If it's reading 62 degrees and the complaint is we're overheating the space, you found your problem. Okay, so I can seal the ductwork, I can insulate the unit to make sure that the temperature here is the same as the return temperature. Okay, but that unit needs to be insulated. It's clearly in the instructions. If we're putting that in an uninsulated space, ductwork needs to be sealed and insulated, and the unit needs to be insulated. Okay. What can I do to cure this? Well, I can go to Follow Me on the remote, but again, don't forget, Follow Me does not remove this sensor from the equation. It'll make this better. We'll talk about there's a remote sensor, a button sensor we can put in. And what it is just a sensor. So we go into the control box, we unplug the return air sensor, we mount the sensor in the space, we've eliminated the return air sensor. Or we can switch to the 24-volt interface. and use a standard thermostat. Okay. Ceiling cassettes. Okay, again, they have a minimum, this pump can only raise the condensate so high. But this clearance is here. To any obstructions, look here, 40 inches on all sides. All right, and this doesn't look bad, looks like a great installation. However, in this particular unit, I need 60 inches here. I don't have 5 feet right there, do I? So my return air sensor's right there. So what's going to happen? Ooh. I want to recirculate. And so if I recirculate, I can't control the space. All right. What would be the solution for this one? I can block off this outlet. Okay. But again, that's going to cause us control problems, which is a service call. It is troubleshooting. All right. Again, on the grill for the ceiling cassette, there's your temporary or emergency heat button. Okay, here's your lights that will blink for fault codes. Okay, your defrost light, that's pretty simple what the defrost light is. Okay, the floor console. Okay, there's the larger floor consoles can be mounted either on the wall or up on the ceiling. Okay, and here's the front of those. This window here is for the infrared receiver. It is not digital display. So I've got my lights over here for my fault codes, and then there's your emergency or manual button right there. So that's right on the front of the unit. Okay. We're going to talk about controls. We're going to talk about troubleshooting communication error. And one of the biggest things is right here. You're going to see that this S wire between indoor and outdoor is communication, DC. L2 also carries DC communication. If we break either one of these wires with a wire nut, a splice, a crimp connector, a switch, we are going to end up having communication errors. An E1, which we'll talk about in a little bit. But again, these get put in this incorrectly, these condensate switch pumps. So we need to talk about it. We don't ever want to break L2 or S, okay? Because L2 carries AC voltage and DC control signal. S carries DC control signal. So those are both communication lines. If I splice or break those in any way, shape, or form with a flare nut, a wire nut, a crimp connector, a switch, a condensate switch, I am going to end up having a communication error. So if you get a communication error, one of the things we want to look at is, are we breaking L2 or S anywhere, including a splice? If you are, that is your problem. All right, I got to get that all, we put it in and we had to splice it and it's inside a drywall wall and it worked for a year. Well, yeah, it got a little corrosion and it's not working now. Well, how do we fix it? Well, you need to have a single conductor. So the point of this diagram is, if you look, this is the condensing unit. So what I want to do is you follow L1. L1 goes to the safety switch in the pump to the indoor unit. So if we get a fault on the pump, we break L1 and the whole unit shuts down. Okay, if we break L2 or S, it may be okay for a while, but eventually we're going to get a communication error because of it. Okay, so that was actually, we're running a little behind because that was where I had my break intended, but it's okay. Okay, installed above snow load. Another thing we want to look at is frosting issues. Okay, so this picture I just threw in because this is just cool. The indoor unit is outdoor, the outdoor unit is indoor. I think it would have been easier to use a reversing valve in that, but okay. Electrical. 14 gauge stranded wire between the indoor and outdoor unit. 14 gauge, 4 conductor, stranded wire. Well, we ran solid, you're going to have communication errors. Or if you are getting at fault, or I have had a job where it's solid halfway and then it's wire not stranded and they're getting communication errors. That is your problem, all right? So a splice in that wire, any break. So 14.4 stranded, not solid. Why can't we use solid? Because the voltage travels down the surface of the wire and a stranded cable has much more surface area than solid. Okay, so no splices, no switches on L2 or S ever. Now, if you work in certain cities like Ann Arbor's one, and they say, well, I want to disconnect that indoor unit, then we need to go with a 15 amp single pole double throw wall switch. Okay, don't use a little metal switch. You want to use an actual wall switch, single pole, triple throw, because that 15 amp switch shouldn't have any resistance. So we shouldn't have any faults. Okay, so again, if you have to break for any reason, break L1 only. Okay. So again, this cable, this is the stuff we all sell. That's 14.4 stranded, which is fine. This metal clad stuff should be fine. Again, you have 4 conductors stranded, but no splices. Okay. On the 3, 4, and 5 ton units, they also use an 18.2 stranded shielded communication cable. Okay, so just be aware of that, because the chances are you don't put a lot of 3, 4, 5 ton light commercial units in, but they also require the 18.2. Okay, this is the job I was talking about. Right inside this box, I have stranded cable coming from inside. I have solid cable coming from all the outside units, and they're all wire nutted in here. And repeated communication errors. The only fix for that is to get rid of those splices. Okay. And the wiring on these things are polarity sensitive. L1 has to be the same as it is here. So whatever's, if you're using black wire here, it has to be the same here. L2 here has to be connected to L2 indoors. S here has to be connected to S here. If they're not, we're going to have a communication error and we might take the board out. So that's really critical that we double check that. All right. Here's the light commercial units with that 18.2 wire. And you can see that we got PS1 and S2. Okay. On the multi-zones, you call me up and say, we got a coil frosting on a multi-zone. 99% sure you crossed the wires, or you or somebody did. So this is, if you look here, L1 for port A, L2 and S. We want to make sure they're connected to port A. And again, they're not crossed. L1 is on L1, L2 is on L2, S is on S. All right. If port A got wired to the unit that's piped to port B, what's going to happen is when port A calls for cooling and the valve's open, it's going to send refrigerant to port B. Well, port B's not calling, so the fan's not running and it's going to frost. All right. Now that coil sensor normally would prevent this, but if we're getting frost, it's probably crossed wires. Now I can't stress that one enough. And I get guys, well, they're not crossed. Yeah, they are. I even had one of the guys who used to work for us was on a job. He called me about 9 in the morning. He said, Dave, I got multi-zone. One of those is frosting, the other one's not. The one that's running's not. And I said, you got wire crossed? No, I don't. So he called one of my other guys. They told him the same thing. About noon, he called me back again. I said, listen, you got wires crossed. No, I don't. So by third time, he called me about 3 in the afternoon. I said, listen, I want you to do this one at a time. Turn on port A. Is it working? Yes. Turn on port B, turn off A. By the time we got to port B, damn, I got a wire crossed. Okay, so if you have frosting coil, it's probably a crossed wire. So so be careful of this. This happens a lot. All right, voltage. Okay, 208 to 230, we should have between 187 and 256. That is our allowable voltage range. It used to be in days gone by, we only needed to check that we had voltage, right? Now we have to check what the voltage is. There's places in Ann Arbor where I've seen we're creeping above 250. Okay. High voltage can be a problem. Most of the boards we lose. If we lose a board, we lost a bridge rectifier. Most of the time that was caused by power surges or high voltage. Okay, so this is also something we want to check, is our voltage. Okay, if I lose a control board and I'm checking and I have 248 volts, right? Well, if I have 248 volts on Thursday when everything's running, good chance on the weekend I'm into the 250s. Okay. This is a single phase voltage monitor specifically designed for mini splits, because the mini split sends power to the control boards all the time. It's not like the old split with the contactor, right? Regular split system, the contactor keeps power off the compressor until we try to run the compressor. On these, those control boards are getting line voltage all the time. So if we get a spike, they get them. So this, if you're losing control boards, I highly recommend you install one of these. Okay, what this is there's a voltage monitor / surge protector inside this enclosure. There's also a contactor. So if you get a surge or your voltage is too high, it's going to kill power to the unit. I would highly recommend, even on installs, putting these in. And then it'll also monitor the power. Then I can go back and look at when did it open and did it have a fault, and I can see what it was. So both surge, high, and low voltage. Okay, but if you've lost multiple control boards, I would definitely look into this. Real simple to put in. It's watertight. It goes outside. Okay. So again, we get back. We're still talking about no fault codes. So we checked. We found out installation was a problem. We got it addressed. However we did it. Again, we're not heating properly. We're not cooling properly. We got no fault codes. That means everything else is happy. All right. So stop looking at the board. Stop looking at the sensors. It's not them. All right. Again, it's an air conditioner. So let's check our temperature splits. All right. So we're going to put the thing in cooling and crank the temperature down as low as it will go. If it's 70 in the room and I turn this down to 68, it's not going to go full open, right? These are modulating. That valve's not going to open that far. The compressor's not going to ramp up that much. So we want to turn it down all the way and put it in turbo. Okay, we're going to check our return error. And then we're going to check our supply error. Now, for the return error, I'm going to put a probe up around the return error sensor. And then I'm going to check my supply error coming out here. Now, do not take your probe and stick it into the front of that unit, because you're going to hit the blower wheel and you're going to bust it. I should have a 20 to 30 degree split. If I got a 15 degree split, chances are that unit is low on charge. Crank it into heating, because we should also always check both. Crank it up all the way, put it in turbo, and I should have a 30 to 40 degree split or rise. If I have less than 30, we could be low on charge. All right, and that could be our problem, why we're not cooling or heating properly. How do I check the charge for sure? I take it out and weigh it in. That is it. Now, if I got and again, you got to use some detective work here. All right, it was cooling last summer, but it's not cooling this summer. It's running, but I only got a 12 degree split or an 18 degree split. But it worked last year. All right, all these things are pointing to charge. So the only way to accurately do it is to take it out and weigh it. Okay, I'm sorry, that's what a mini split is. They're critically charged. So I'm going to take the charge out and I'm going to weigh it. And then I'm going to look at what the factory charge is. And if it's low, I have a leak. All right, and I need to address the leak. Now, can we just top it off? No, we can't, because there's no way of knowing what you're adding. You know, you can't superheat charge, you can't subcool charge. Your suction pressure is going to be normal, even though we're grossly undercharged. So you can't, and you can't read head pressure when you're in cooling. All right, so you can't do it. Now, I'm amongst friends here, I know. So I'm going to give you a little cheat here just to confirm. So you're thinking, okay, I'm pretty certain this thing's low in charge. All right. Now you won't find this in the book, and I'm trusting you guys are going to be honest with me here. So what I could do, let's say, all right, the split is really low. I'm going to add a little refrigerant. I'm going to add a couple ounces. Weigh, if you're going to do that, and I know you will, weigh what you put in. So I put in 4 ounces. I weighed it. Ooh, it got better. It's definitely low on charge. Now we got to take it out and weigh it in. If it didn't get better, we confirmed it's not low on charge, then just take out what you put in. All right. Don't randomly just add refrigerant, because then you have no clue where you're at. When you do take refrigerant out, make sure you weigh it. All right. Now, we all worked for this guy. You know, the guy, the super guy. I've been doing this forever. I can charge it. No, he can't. It's not possible. Okay. I work on these, work with these things all the time. It's not possible. There's no possible way to charge this by beer can cold, amp draw, frost line. I'm on all the different things that crazy dudes have told you along the way. You can't do it. The only way to absolute check charge on this thing is to take it out and weigh it. All right. And then weigh it back in. And I don't mean take it out mostly. I mean, take it all out. Recover it all the way and weigh it. Okay. Now, these units are pre-charged for a certain amount of piping. So to know what the total charge should be, you need to measure the piping. And if it's within the allowed limits, then it's just factory charge. If it's beyond what the pre-charge amount is, then it's going to be factory charge plus the pre-charge amount. So all units are pre-charged for 25 feet. If I look here, they're all charged for 25 feet of line. So 10 feet to 25 feet, I don't need to add anything or take anything out. But if I go beyond 25 feet, then I need to add. And if I look on the chart here, depending on the piping size, it could be 0.16 or 0.32 ounces per foot beyond 25 feet. If I get into a multi-zone, you can see an 18 is charged for 50 feet, 24 is for 74, for 100, and so on. If my total piping length is beyond 49 feet, then I need to add 0.16 ounces per foot. So again, I'd have to measure my piping to determine if I needed additional charge. And maybe that's it. Maybe the installer didn't add the additional charge. Okay. Error codes. So up until now, we talk about temperature control issues, which are related to installation. Charge. Everything that we looked at has, the unit thinks it's fine. Because if the unit does not have a blinking light, everything is good. The sensors are good. The compressor is running. The fans, because any of those fail, we're going to get a fault code. All right. So I get a blinking light. So I'm going to check we're going to start looking at our fault codes. Okay. First of all, these 2 dashes here. I just got this call the other day from one of our TMs. Hey, so-and-so heating just put in a multi-zone. One of the heads keeps getting double dashes. Well, remember when I said you put them all in auto and one goes for heating and one goes for cooling? The heating call is the priority. So the unit that's in cooling is going to go to double dashes. Doesn't mean anything. Just once the heating call is satisfied, it's going to switch to cooling. Okay. You won't find that in the book, the double dashes. It's not really a fault. It just means conflict of mode, meaning one unit is in cooling, one unit is in heating. All right. So it's not really a fault at all. DF. I can show you the email. I got this from my branches yesterday. Hey, so-and-so just put what's DF mean?
Hey Dave, are you on still? Looks like we lost Dave for a quick second. I'm gonna try and get him back.
Everybody still there?
There we go, Dave. We can hear you now. Yep, people stayed on. They did
All
great.
right, good. I apologize for that. I don't know what happened. I think my power cut out for a second and
No worries. Let's see here. It looks like you should still be able to share your screen just fine.
yeah, I'm already did. I just got to get back to where I was here.
Perfect.
Okay, so slide. Okay, so I'm back. I'm sorry about that. Apologize for the technical difficulties. Electronics. So anyways, this coil right here, there's nothing wrong with it. You'll get that call. The coil is completely covered with frost. Is it still heating? Don't worry about it. Okay. There's nothing wrong. Within about an hour, this went to frost. It completely cleared that. Okay. But you will get the call. The coil's frosted. Now, look at this coil. Is that a defrost problem? No. Think of an air conditioner. This is the evaporator. If you walked up on an A coil in a furnace and you saw this ice like this, what's wrong with this unit? Is that a defrost issue? No, this is low in charge. Okay, so again, it's still an air conditioner, but in heating, the outdoor unit becomes the evaporator. So that is not a defrost issue. That's a low charge issue right there. And the complaint was, well, it doesn't defrost properly. Remember an A coil. I'm sure you've all seen it. You got a low charge A coil, right? The inlet's big block ice because we're boiling the refrigerant off too soon. Okay, so you should have a nice even layer of ice. Don't care how thick it is, as long as it's still working, there's nothing wrong with it, but it should be even. This is low in charge. That is not a defrost issue. Okay, so just know the difference because it is still an air conditioner. All right, so again, we look at fault codes on a high wall, and if I get a high wall indoor unit, I'm going to look at the service manual for the indoor unit, and I'm going to look at the fault codes. E1, indoor unit and outdoor unit communication error. All right, remember our three wires, L1, L2, and S? There's either a problem with the wires, we lost DC power on the indoor unit, or we lost DC power on the outdoor unit. It's one of the three. Okay, and we're going to look at how to troubleshoot that. E3, indoor fan speed. That means the fan motor wasn't coming up to speed. We probably have a problem with indoor fan motor. Okay, so most of these E4, T1 sensor's bad. E5, T2 sensor's bad. EC, refrigerant leak detection. This thing is damn near empty before that comes up. Outdoor air temperature, condenser temperature. So most of these are pretty cut and dry. Outdoor fan speed out of order. ITM, that means we have an inverter issue. We're going to look into that. Okay. high temperature protection of the compressor's overheating. Why would a compressor overheat? It's just air conditioning. So now on a cassette and ducted to floor consoles, okay, here's the codes there. E1, we have a communication error between indoor and outdoor. And I'm going to tell you, indoor board is bad, outdoor board is bad, or the wire is bad. All right, don't count that wire out. We're going to talk about that as we move on. If we get the fault codes from the outdoor units, make sure you look in the manual for the outdoor units. All right. And again, if you're doing multi-zones, make sure you always check the codes on the outdoor, not just the indoor. Because these codes it'll send you in the wrong direction. Okay. Also with this, and this is pretty cool right here. If I look close, there's my display, right? See it? Over here is SW1. It's a button. Okay. What am I going to do with SW1? SW1 is going to allow me to look at all kind of different stuff. Okay. So I can actually look at all my sensors. I can actually read all my sensors from right here. All my return air sensors, all my coil sensors, my outdoor ambient, all my expansion valve angles. I can read all that from right here. So we'll see that in a minute. All right, so here's the fault codes for the outdoor units. Again, most of these are pretty easy. E2 communication, check wiring. E3, IPM, which we'd have to look at. High pressure, low pressure. I mean, these temperature sensor fails. Most of these go to the book. The third, high pressure, low pressure switch. It's air conditioning. But if you get into some of the tougher ones, like an E0, E2, E3, go to the service manual and start following the troubleshooting guide, and we'll see it in a second. But the biggest thing is use the right troubleshooting chart for depending on where you get the fault code. All right, here's the service manual for the multi-zone outdoor unit. Where do I get these? Well, if you have access to HVAC Partners, you can just go on there and download them. Now, there's one for multi-zone, there's one for single zone, there's one for light commercial, and then there's one for every single fan coil. So it's not necessarily something you should keep on hand all the time. Also, there's the Bryant Service Tech app on your phone you can get, or call any of the branches, and any of our branch people should be able to pull this up for you and email it to you within about a minute. Okay, so if you get a fault code, I ask you before you call us, get this manual and let's get to the fault codes. All right, so E1. Okay, I'm going to touch on some of the more difficult yet very common fault codes. E1 is a communication error. So this is right out of the manual. And you can see it says indoor unit does not receive feedback from outdoor unit within 10 seconds. So we're not talking. So there's a DC signal goes between indoor and outdoor, right? So either indoor unit's bad, motor, or either indoor board's an issue, outdoor board, or the wire. Okay, so if I go into the service manual, here's this little flow chart here, and it's going to tell me what to do. So first thing it says is connect the red lead plus to your meter on L2 black, and or on L2 put the black on S. So I'm going to go in here. I'm going to put see, I got my red lead on L2, my black lead on S. All right, see that? And I'm going to check my DC voltage. Okay, that's my communication. Now, this note is further down the page. It says, when the AC is running normally, the voltage, meaning the air conditioner, not voltage, the voltage moves alternatively between negative and positive 50 volts. All right. So what that means is on my meter here, this should be switching from negative to positive, and the voltage should be jumping all over the place. It should look like total chaos. I mean, 9, 50, 80, 12, 50, 40. But it should be jumping back and forth, and it should be going negative, positive, negative, positive, negative, positive. That's the normal signal. What if it's not? If the outdoor unit has a malfunction, So the problem is in the outdoor unit, the voltage moves alternatively with only positive value. So we're only reading positive, the problem's at the outdoor unit. If the indoor unit has a malfunction, if the problem is the indoor unit, then the voltage will have a fixed value of about 10 to 13 volts, meaning it's just sitting there. It's not modulating at all. Pretty simple. So if it's all positive, the outdoor board is a problem. Let's go look at the outdoor board. How do I check it? Remember looking for DC volts on the board, looking for AC volts, looking for the lights. If it's sitting there at like 15 volts DC, not moving at all, it means the problem's the indoor unit. Now, what if the wire's the issue? Well, I would need to check this at both ends, right? Because the wire is what communicates between the two. So if I check at the one end, at the indoor unit, and I'm only getting positive, and I check at the outdoor unit, and I'm only getting the steady, the problem's in the wire. All right. Now, E1 sometimes can be kind of tricky to find, but it's actually pretty simple. So if I'm not getting the same reading at the indoor unit and the outdoor unit, then I'm assuming it's in the wire. So now I can ohm out the wire, ohm it out to each other, ohm it out to ground. I should have I should have full resistance, infinite resistance between the wires and the ground. If I have any flow at all, there's a problem in the wire. All right, whether it's got a little pinch in it, whatever. So I should have no resistance to the wire, to each of the three other wires, or to ground. Okay. Are they crossed? Again, we talked about this earlier. If I have L2 on the indoor going to L1 on the outdoor, now my wiring's crossed and I'm still going to get a communication error, right? So double check that wiring. And I've been on jobs where guys have double checked it. But I get there, it's still crossed. So sometimes, easiest, take a picture, go to from the outdoor unit, go to the indoor unit and double check that those wires are not crossed. Okay, because you will get a communication error. All right, so again, just follow on down the list here. So we check that, okay, do we have the DC voltage? Check all the wiring. Again, we can ohm it out. Measure DC volts. So remember, we can go to the capacitor to see if we have our DC volts, to see if we lost the board. Obviously, check our AC volts. All right, so right on down the line. So just follow this little flow chart, follow the little notes, and this will walk you right through it. Okay, again, you can call us, but until you dive into this stuff, you're not going to start to learn it. So let's take a look at the wiring diagram again. This is in the manual. So I'm going to find, here's my L1 and L2 coming in. So do I have, voltage here? And then I'm going to find my, on the board here, there's light on the board. Are the lights on the board on? If they are, that means I have DC volts. If they're not, then I don't. Okay, so now my inverter board, so my L1, L2 in here, L1, L2 out here, they come to right here. Do I have 230 volts here? Yes. I can go to my capacitors. Do I have my DC voltage? No, then I know the board is bad. So it's pretty much that simple. Do I have AC volts coming out? They're going in, do I have DC volts coming out? If I don't, then it's that board. That's what caused that. All right. Now, if I lose the board, why did I lose the board? All right, I got AC power coming in there. I have no DC power on this board anywhere. The display is dead. So what took it out? So let's take a look on this board. What could possibly take this board out? Well, the four-way valve is AC power. It's not that. The heaters, one's crankcase, one's pan. Those are 230 volt. It's not that. The expansion valves are DC. Could be them. So we can look at the expansion valves. I just had this happen a couple weeks ago. Would replace the board. It would last for about 30 seconds. It would go. We had a short in one of the expansion valves. So basically, you just ohm out your expansion valves. The thermistors could be, but likely those aren't going to cause it to take the board out. Okay. E3.
Hey, Dave.
Yeah.
We got a quick question.
Yes, sir.
So the question is, the person stated, I have shorted communicating wires and shorted fried boards. Have they considered fusing communication wires?
Well, the communication wire, the communication side, if you just short the communication, then normally it's not going to damage anything. What it is when you cross L1 and L2, you just sent AC power down the DC bus. And there's not really a way they can protect from that. So, again, and if you're just crossing communication, the DC to ground, it doesn't normally hurt anything. But when you cross AC to DC, you're going to damage things. So there's no way they can protect from that. So we just need to be careful of that. And before you unplug or plug anything in, shut the thing off and give it 5 minutes for those capacitors to discharge. Okay, because sometimes, and I'll be honest, I've done that. I'm not patient enough. And you go to unplug something on the DC bus, momentarily short it, and then you fry something. So do not plug anything in or unplug anything until the power is off and the capacitors are discharged. So give them 5 minutes. And I know we're in a hurry. We're trying to be impatient, but that'll actually do some damage too. Okay, so so again, just be careful when you're wiring these. We don't get that wire crossed up, but I said, in the event we do lose a board, we have to figure out what happened to it. Now, if you call me and say, Dave, I have anyone, we start talking, you crossed those wires. Be honest. Okay, we'll get a good laugh out of it. We'll change the board. We'll move on. But don't make me, talk to you for 45 minutes to find out and say, well, we crossed the wires at first. Do you think that did it? Okay. So again, to troubleshoot it though, just like that ignition module, do I have AC power coming in? Do I have DC power on the board? If I don't, what took it out? Chances are it was high voltage coming in. Again, this expansion valve one I just had, that was a new one, but it did take the board out. Crossed wires during install, obviously it'll do it as well. Okay, there's all our thermistors. We can do an ohm meter with those. We already talked about that. Expansion valves, I ohm those out. The inverter, I can ohm that out with the power off. So it's actually, most of the stuff is, as you kind of get to understand it, it's really not that bad. Okay, E3. Again, if you look, and I know it's a little harder to see on a computer here than on a big screen, when the indoor fan speed is too slow. So this thing actually monitors indoor fan speed, and this one comes up every so often. So if the indoor fan motor is not coming up to full speed, here's some of the causes. Wiring mistake. Well, did it work yesterday? Yes. Okay. There's not a wiring problem. Again, we got to, put some common sense in here. Okay. Chances are the motor's bad. All right. If you're getting an E3, but again, you got to kind of look at the possibilities here and when did it happen? All right. But chances are the fan's bad. It's not coming up to full speed or it's not coming on. So it'll sit there and tick away. Again, I turn on after 5 seconds. Is it still displaying the error code? No. The unit operates normally. Yes. Shut the power off, rotate the fan. So does the fan spin freely? Is it jammed up on something? No. Determine the cause. Okay. Is there something in it? Is it dirty? Is it, check fan motor wires. Are they good? Yes. Okay. And then last but not least, the fan motor's bad. Okay, so just follow these flow charts. And again, as you do more and more of these, you're going to get a little more accustomed to them. Again, the biggest trick is just not being afraid of these. It's an air conditioner. This is what we work on, right, guys? It's got some really cool features, but we got some great troubleshooting. And until we start to get comfortable with them, they're always going to be in this mystery thing. And every once in a while, you're going to get on a real SOB, like the one I had with that expansion valve. The contractor had owned them all out. I was on the job, and this is the first time I've ever come across it. And we ohmed them out again, and one of them wasn't completely shorted, but we didn't have that consistent resistance, and so the valve was the problem. Okay, P6, the infamous inverter error. All right, this is another, we get a P6. Now, P6 is telling us that the inverter, which sends the power to the compressor, is either drawing too much amperage or it's getting too hot. So for some reason, that compressor is working too hard. So again, when we look at the causes, we have to think about, did this unit run before, or did we just install it? Okay. Refrigerant flow right here. So if I look at this one, refrigerant flow, are the valves open? So if you get a P6 on startup, you have a refrigerant flow issue and the compressor is pumping against a closed valve. All right, so again, when you look at these troubleshooting guides, they're kind of assuming this unit ran at some point. So let's say the unit ran great, we get a P6. So I'm gonna start looking down the troubleshooting guide here. And first thing it says is check my DC volts. Remember, it's capacitor. And then I'm gonna go down the line, check all my connections. I'm gonna power the thing down, do that test for my inverter. Okay. Remember that the test, and we'll see it again. There's actually a picture in the service manual of it. But take a look at this, because again, P6 indicates the inverter is getting too hot or drawing too much amperage. So if I look at the picture on the left, that's the compressor insulation jacket. All right, because P6 is either indicates I got a blockage causing the compressor to work too hard. My inverter is actually bad, or my compressor's a problem. Now, just like any other compressor, I can ohm it out, but I can't check it mechanically inside, right? Every air conditioner we work on, we can't mechanically check the compressor. We can electrically test it, but we can't mechanically check it. So you got this inverter issue. We go through and do our inverter test, like I showed you earlier, which is in the service manual. That's good. Pull the jacket off the compressor. The one on the left is the clean jacket. That's what it should look like. The one on the right, that compressor is the problem. That compressor's working too hard. So there's some type of internal damage inside the compressor. This thing could have run low on charge for a while. We could have ran against closed valves. That's happened. Multi-zone, some valves get left closed. The thing runs for a couple of days that way. And the weird thing is the compressor will run some, but as it tries to ramp up to full speed, it'll go off in an inverter error. Okay, so one of the things I'll ask you to do is pull the compressor jacket off. Is it brown? Yes, it is. Well, the problem is the compressor, not the inverter. Okay, another thing we can do is on an inverter error is put an amp probe on the compressor. Because again, remember it's actually has AC signal again, and see if the compressor is starting, or because you might get some amperage, because the compressor might be able to run at lower speeds. It's not till it ramps up that it starts to overamp. Okay, so to confirm that the compressor is running, how do I test the compressor? That is actually a 3-phase compressor coming off the inverter. We're actually creating a 3-phase voltage. So we just ohm the compressor windings to each other, and we should have consistency. So all 3 windings should ohm out the same, basically. If you got one way off from the other 2, the compressor's a problem, just like any other compressor. Ohm it out to its shell, see if it's grounded. But remember, when you plug this back in, this is polarity sensitive. U, V, and W on the compressor have to be to U, V, and W on the board. Okay. All right, here's that test I told you about earlier. This is actually a picture out of the service manual. And it's going to show you exactly how to test that inverter. So you power it down. All right, just like I showed you earlier, you're going to put the red lead on P, then you're going to go UVW, then you're going to swap the red lead to negative, and then do UVW again. And your resistance should all be the same, or virtually the same. It might be 0.56, 0.6, 0.53, virtually all the same. That's pretty much that simple. Do you have AC coming in? Do you have DC at the capacitors? Do this test. We just tested the inverter. Okay. Now, another thing you could do is, this is a 3-phase compressor, right? So this 3-phase voltage coming out here. We don't know what the voltage is, but it should be the same. So like I had a guy yesterday check. So he put his probes on W to V, wait for the thing to time out. The compressor tries to come on. He got 66 volts. Then he went from V to U, he had 66 volts. From W to U, he had 66 volts. So the inverter was putting out a consistent signal. So the inverter was working. This problem was the compressor. Okay. So any questions on that before I move on? I know that's a little confusing, but it's really not that scary. The service manual will walk you right through that. It's a 3-phase compressor. We can ohm it out. Follow these tests here, but again, remember, they're making the assumption that this unit ran at one time. So if you're getting a P6 on startup, you got a valve closed, you got a kink line, you have a refrigerant flow issue, the compressor's trying to pump. If you've got a P6 on a unit that's been running for a while, that's what this is referring to. And then we have either an inverter error, a problem, or a compressor problem. Okay, and again, this little jacket is a telltale sign that the compressor is a problem. And the compressor could be running, just not ramping up all the way. Okay. P1, low pressure trip. Or P1 high pressure, P2 low pressure. Okay, these are pressure switches. They're not transducers. They're normally closed. If they're open, the pressure got too high for some reason. These are air conditioners. Let's take a look at it. It's tripping on high air pressure. Is there non-condensables in it? Did someone overcharge it? Is the condenser dirty? Is tripping on low pressure? Is it low on charge? We got dirty filter someplace. Do we got an expansion valve that's not opening? Okay. Isaac, do you say something? Oh, I guess I'm going nuts. Okay. Anyways, last but not least, we're going to look back at this little digital display here. Oh my gosh, we're way over. Apologize for that. This little digital display, this is on the multi-zones only. We go to this little push button here, and this is stuff I can look at. Indoor unit capacities, demand from each indoor unit, the frequency going to the compressor. We can read all the thermistors, indoor thermistors, outdoor thermistors, expansion valve positions. I can read all of it. My last fault code I can read. So if the fault was cleared, I can read that, all from that outdoor unit. Now, when I'm pushing these button 28 times, the display will keep track, 1, 2, 3, 4, 5. And then when you let go, it'll switch and give you that reading. All right, here's the service manual. You will be getting these things sent to you after the class. This is the service manual for the wireless remote. And the last page, we have something called the point check function. What that'll do is on a high wall units, multi-zones, I can do it from the outdoor unit, but from the high wall single zones, I can do it from the display on the high wall. I press the LED button 3 times, press the swing button 3 times, you'll hear a long beep, and the display will change. That's a T1, it looks like R1. T1, and in a second, it's gonna show in Celsius what that return air sensor is reading. Okay, so I can actually look right on the front of the unit and see what the sensor's reading. All right, so is that a pretty cool function for testing a thermistor? So you put a thermometer up there, you see what this reads, you actually see what it's reading, and they should be pretty much the same. So if T1, and then if I scroll down to T2, it's gonna give me the indoor coil temperature. T3 is outdoor coil. T4 is outdoor air. T2B, you remember on the multi-zones, every suction line has a sensor. TP is the compressor discharge. Target frequency, that's what the unit's calling the compressor to run. This is FR, is what the compressor is actually running. Down here, expansion valve angle, LA. Now it's a 250, it's for a 480 position valve. So if it's at 250 pulses, that sucker's half open, right? It's calling for a lot. What if I'm not cooling much? I only got a 15-degree split, and my expansion valve was half open, but my compressor's ramped down really low. Well, definitely all point low charge, right? Got high superheat. It's just an air conditioner. Okay, so this is kind of a cool feature. This manual, it's one of the things you'll get after the training here. So this is on the last page, this point check function. Again, great troubleshooting things. Okay, I'm sorry I went a little long. I had that little difficulty. I know it's 11:30. We're supposed to be done before now, but I apologize for getting windy and my little technical problems. So the book, the service manuals you can either get from HVAC Partners. There's the Bryant Service Tech app that you can get on your phone, or you can get it from one of our branches. Just give them a call, tell them what you need. They should be able to email it to you. All right, and I really ask that you guys start diving into those manuals and try to work the stuff out yourself. Give us a call. We're here to help. But until you start to get comfortable and familiar with these things, you're never going to. And trust me, whether it's a Daikin, a Mitsubishi, a Bryant, a Midea, they all work fairly much the same. So as you start to get to know one, you're going to start to understand all of them. They all got their intricacies, but okay. So that being said, hopefully you got something out of today. I know I hit you with a whole lot in 2 hours, and it's a little harder to do this online than it is in person when I can show you things and pass stuff around and we can do some testing, but this is what we have now. So are there any other questions? Have I answered everybody's questions?
There's no new questions in the chat.
Okay, so let me close this out, stop share. All right, so one of the things you're going to get is you'll get the critique. It's going to come through. They're going to ask you about the class. Now, this again is training online is a whole new thing for everybody. So, we're looking for your feedback. We tried to keep it at 2 hours because it's hard to keep your attention otherwise. So if you could take a few minutes and fill that out, that'd be tremendously helpful. If you are on your way to your call in an hour and you say, damn, I should have asked him this. In the chat, I just put up my email address. It's davep@Behler-Young.com. And here I am just putting my phone number up there as well. If you want to text me a question or email me a question or call me, please feel free. Again, the biggest thing is if you're looking for help and I'm not available, reach out to one of the other guys. Your branch should be able to, get a hold of your branch. They should be able to get you a hold of somebody. Don't just wait until I'm back. Because again, this morning I'm tied up all morning. So if you were trying to get a hold of me at 8 o'clock this morning, you'd be waiting. So we don't want you to do that. So, like I said, please fill out the critiques. We really, really need those to try to keep improving this because this is all a weird thing, this online training, but I think it's part of life now. So if you could please take the time to do that. And unless there's any other questions coming through, and I don't see any. Somebody said good stuff. Thank you. Well, I appreciate it. Good feedback's always enjoyed, but bad feedback is good too. So don't be afraid of that. Because again, it's going to help us make this better. So just be honest. So Isaac, anything else?
Nope, all good on my end. Thanks, Dave.
All right then. Well, then I guess everybody probably has other things to do than sit and listen to me anymore. So, head on out to work, I guess. Have a great day. And like I said, if you have any questions, either email me, text me, call me, whatever. I'm here to help you. And thank you. Thanks, for joining us.
Thank you.
Thank you.
Yep. Have a great rest of your day.
You too.